So, I think in my last class I talked about, so I have already given this proof that the necessary and sufficient condition uh, for separability of two mode Gaussian states. And this so this proof basically it is like this determinant of A into determinant of B plus this quantity, what is that, yes, plus 1 by 4 minus magnitude of determinant of C whole square minus trace of Aj, Cj, Bj, C transpose J is greater than equal to 1 by 4 determinant of A plus determinant of B, where of course your covariance matrix. So, these two mode Gaussian states having covariance matrix as gamma, which is A C C transpose B, and J is here I sigma y. So, this is what we have proved, and in order to prove this thing, what we have used two results. One is that so number one is that I mean I have used for two mode Gaussian state, but this is true for any Gaussian state. So, a two mode Gaussian state, this two mode is for our purpose, this is not I mean this can be any mode. Okay. So, this two mode Gaussian state having covariance matrix gamma is classical in the quantum optical sense. Okay. Is classical if and only if yes, if and only if gamma minus half 4 cross 4, this is greater than equal to 0. Okay. So, this is one result, and again if it is I mean this 4 cross 4 because I am considering two mode, and the other one is this one. Any, so here also you can say any two mode Gaussian state having covariance matrix gamma is equal to A C C transpose B, okay, is separable if determinant of C is greater than equal to 0. Okay. So, yeah, so these are the two things which we used in order to prove this result, and I think in my last class I have proved this thing, that if determinant of C is greater than equal to 0 for a two mode Gaussian state, then the state is separable. Okay. And this we have not yet proved, that I mean any 2 mode Gaussian state, I mean this is not just true for 2 mode, you can take any mode. So, accordingly you will have to change this thing. So, this is classical in the quantum optical sense, if and only if this gamma is greater than or equal to half of this identity. Okay. So, yeah, so this is what so this we have proved. So, let me prove this part. Okay. Right. Okay. So, let me see. Just a minute, I will just try to see. Sorry, I mean, yeah. Where is the proof? Just a minute. Yes. Okay. Yes. So, this is what I am going to prove now. Okay. So, any 2 mode Gaussian state having covariance matrix gamma is classical in the quantum optical sense, if and only if this is the case. Okay. Right. So, let me proof of 1. Let me look at that. Okay. So, let us take rho is a like this is a 2 mode Gaussian state. Okay. Right. So, this is a 2 mode Gaussian state and having covariance matrix gamma is equal to A C C transpose B. This is the usual one. Okay. Right. Okay. So, then let us see that the p distribution. So, p distribution function of rho. So, this p distribution is p rho alpha 1 alpha 2, right, where alpha 1 alpha 2 are complex numbers, right. This is the p distribution. So, then I can write rho 1 2 as alpha 1 alpha 2 belonging to C, d square alpha 1 d square alpha 2 p rho alpha 1 alpha 2 projection on this coherent state alpha 1 tensor product projection on coherent state alpha 2, right. This is the way I can write any state in terms of the p distribution. Okay. Right. So, now you select this okay. So, basically if I now apply this local symplectic transformation. So, now you apply S local, okay. So, which is S1 0 0 S2, which is an element of SP2R tensor product SP2R. So, which is a local symplectic transformation on rho 1 2. So, this of course, will not change the separability or entanglement property of this state, because this will be local unitary transformation. Okay. And so basically we choose this S 1, which is a symplectic transformation, which is an element of S P 2 R. So, to choose this S 1 like this. So, this is a rotation cosine theta 1 sin theta 1 minus sin theta 1 cosine theta 1. Okay. And similarly, so maybe I will call it S j. So, this is j, j, j and j. So, j is equal to 1 and 2. So, this is what you choose. Okay. So, this you know that this will take x j p j is for the jth mode. Under this action of S j, it will go to x 1 cosine x j cosine theta j plus p j sin theta j and minus x j sin theta j plus p j cosine theta j, right. This is what it will have, and the corresponding unitary representation. This is u of S j, corresponding unitary representation, and this you can take as exponential of minus iota theta j a j dagger a j, right. This is basically the rotation. Okay. Right. So, then this gamma under this S local, it will go to S 1 0 0 S 1 S 2, sorry, this should be S 2, yeah, S 2, then gamma then S 1 transpose 0 0 S 2 transpose, which in our case is S 1 A S 1 transpose, S 1 C S 2 transpose, S 2 C transpose S 1 transpose, then S 2 B S 2 transpose. Okay. This is how it works. Okay, good. And now, because this is a symplectic, this is a covariance matrix, we know that A and B, in fact, A and B, these are all positive, in fact, they are all greater than equal to half. So, that we know. So, therefore, I can choose these rotations, because these are Hermitian matrices A and B. So, I can choose these, because this is rotation, I can take it to be a diagonal matrix. Okay. So, this is like A 1 and A 1 prime, where both of them are non negative, in fact, they are greater than equal to half, and similarly this I can choose. So, here A 1 and A 1 prime are greater than equal to half. Similarly, this I can choose as diagonal of B 1 and B 1 prime, where both B 1 and B 1 prime are greater than equal to half, because of the uncertainty relation, right. Okay. So, this I can choose, right. Okay. So, therefore, you see that under this rotation, so u of, so of course, you will have to be careful, because yeah, at the operator level this is how it works. So, basically this you can think of as something like this, u of S 1, then x j, not u of S 1, sorry, what should I so this is u of s j x j u of s j dagger, and similarly this is u of s j p j u of s j dagger, right. This is how it works. So, now if I want to look at, so that is the Heisenberg picture. So, I will take this at the Schrodinger picture, u of s 2 dagger, then rho 1 2, then u of s 1 tensor product u of s 2. If I do that, so because of this expression, I know that this will be alpha 1 alpha 2 belonging to C, d square alpha 1 d square alpha 2 p rho alpha 1 alpha 2, and now this is a rotation. So, this is basically what you are looking at is the action of u of s 1 dagger on alpha 1 u of s 1 tensor product u of s 2 dagger alpha 2 u of s 2. Okay. So, that is what you are looking at, and because this is a rotation. So, this is basically under the harmonic oscillator Hamiltonian. So, what happens is this will acquire a phase, right. So, this will be basically alpha 1 alpha 2 belonging to C d square alpha 1 d square alpha 2 p rho alpha 1 alpha 2 into this will be basically alpha 1 e to the power I theta 1 alpha 1 e to the power I theta 1 tensor product alpha 2 e to the power I theta 2 alpha 2 e to the power I theta 2, right, because this is the phase it will acquire. Okay. Yeah, basically this is rotators, and that under harmonic oscillator Hamiltonian a coherent state will become another coherent state with a phase change, overall phase change. Okay. So, that is what it happens. Okay, good. And because this is a these symplectic transformations you can achieve through quadratic Hamiltonian, these rotations, it will not change the Gaussianity property of the state, neither it will change the separability or entanglement property of the state, right. And this you can write as you can rename these as alpha 1 prime, these as alpha 2 prime, and this will not change. So, basically this will be again alpha 1 prime alpha 2 prime belonging to C d square alpha 1 prime d square alpha 2 prime. Now, you can, so this is a function of alpha 1 alpha 2. I can replace alpha 1 alpha 2 by alpha 1 prime alpha 2 prime accordingly, and let me call these as p rho tilde alpha 1 prime alpha 2 prime. So, this is actually these are same, these two are same. Okay. So, I have just replaced alpha 1 alpha 2 by alpha 1 prime alpha 2 prime, and this is alpha 1 prime alpha 1 prime tensor alpha 2 prime alpha 2 prime. So, what does it mean actually? It means that this transformation, which is a local symplectic transformation and which is also rotation, it does not change the classical nature of the state. If this is non-negative everywhere, this is also non-negative everywhere, right, because these are same.
But when we did this relabeling of the basis states,
yes,
change.
no, this replace alpha 1 by alpha 1 e to the power minus I theta 1.
Yes.
Okay. So, that I am calling as rho tilde, a p tilde. Okay. So, therefore, these are same. So, therefore, if this is non-negative, this is also non-negative. Okay. So, under this rotation, I mean local rotation, the state classicality of the state will not change. Okay. So, if initially it is classical, it will remain classical. If initially it was non-classical, it will also remain non-classical. Okay. Right. Okay. So, this transformation, this local symplectic transformation does not change Gaussianity, does not change entanglement or separability, does not change classicality, non-classicality. Okay. Right. Okay. So, now let us call this as your which one? Yeah. So, this let me call it as gamma prime. Okay. This is my new covariance matrix. I mean basically this is the covariance matrix corresponding to the state, right. So, if you call it as rho 1 2 prime, so gamma prime is the covariance matrix of rho 1 2 prime. Okay. Okay, good. So, you see that initially this gamma, because it is a covariance matrix, this plus iota by 2 omega greater than equal to 0, right, uncertainty relation. Now, I have changed it to gamma prime. Okay. So, now basically what you will see is that the gamma prime plus iota by 2 omega also greater than equal to 0, because this has to be the case, but that is okay, that is fine. But now if I see that, let us say that gamma is, because this is what we have to prove, let us say that gamma, let gamma is greater than equal to half identity. Okay. Let us say, then how did you obtain gamma prime? By applying these rotations, local rotations, which is again a unitary transformation. So, therefore, this is equivalent to saying that gamma prime is greater than or equal to identity, right, half identity. Okay. So, if I can prove for this gamma prime that this is the case, then it is equivalent to proving that gamma is greater than or equal to half identity. Okay. Right. So, okay. So, let me erase this part. Maybe I do not need this, I only need to prove this part. Okay. Now, what I would like to prove that if the original state is classical, then this is the case, and vice versa. If this is the case, then the original state is also classical. So, that is what we are going to prove. Now, so for that, let me just without going through much details, let us look at the gamma matrix of this coherent state. Okay. So, alpha 1 tensor product alpha 2 alpha 2. So, the tensor product of two coherent states. Okay. So, if I look at that, then you know that its j kth entry, it will be trace over this thing, right, anti-commutator of this R j minus R j and then R k minus average of R k. This is of course with respect to the state, and then your this one alpha 1 tensor product alpha 2 alpha 2, right. This is what we will have. Okay. So, this I am not going to do it. Basically what you will see that these are all zeros, average values with respect to the coherent state are all 0. So, I am not going to do that. So, what you will figure out is that this is nothing but delta j k, okay? Not delta j k, half delta j k for j and k is equal to 1, 2, 3, 4, right. So, this if you calculate, this is what you will get, right. So, what does it mean? It means that for this coherent state, tensor product of these coherent state, this is equal to half identity 4 cross 4, and this is a classical state because this is tensor product of coherent state, okay. And for this classical state, this is what you get, okay, right. Okay, good. Now, let us look at a bit more. So, now let us look at gamma rho 1 2, which is my original state, right. Now, if you remember this j kth entry, this should be, so here is a is a caveat, but let me come to this later. This is now gamma alpha 1 tensor product alpha 2 its j kth entry. Do you agree? Because this is what you will have, right. And because this is delta j k, so therefore, half delta j k. So, therefore, this will be your half delta j k times alpha 1 alpha 2 belonging to C, d square alpha 1 d square alpha 2 p rho alpha 1 alpha 2, right. But now you know that because this is a p distribution function, this integral should give me 1, because this is a quasi probability distribution, right. So, this integral should give me 1. So, therefore, this is half delta j k, right. So, what does it mean? It means that for any state rho 1 2, so this gamma rho 1 2 is equal to half identity 4 cross 4. Now, this is, so as I said, there is a caveat here. Now, this is too much to ask, right, because this cannot be the case, right. So, there is something wrong. What is wrong? Wrong is the case that this function is not, most of the times this is not well behaved function, and in fact, for Gaussian states we know that this is, I mean, this is either finite, in which case this is classical, or it is singular. I mean, there is nothing in between. Okay. Now, if it is singular, you cannot do this thing, this does not make sense. Okay. So, therefore, you cannot claim this thing. So, you can do this provided, so this is allowed provided p rho alpha 1 alpha 2 is a probability distribution, because I said there is nothing like this can be negative, nothing like that, I mean negative but finite. This is either positive I mean semi definite, or this is singular for the Gaussian state case. So, therefore, if this is a probability distribution, of course, what you have done is correct, right, and in that case it is indeed true. So, this means that gamma of rho 1 2 is equal to half identity 4 cross 4 if rho 1 2 is classical, right, because if it is classical, then this is a probability distribution and then you can do this, okay, right. So, you see that if rho is a, so in our case this is a Gaussian state, fine, I mean this is classical Gaussian state. So, if rho is a classical Gaussian state, then this is what you have, and therefore, of course, this condition is also satisfied. This is satisfied, this is satisfied, that is fine. Okay, good. So, one part of this result is now we have proved that if a rho 1 2 is a classical Gaussian state, then this is of course true.
But then we don't have the greater than, it's just equal.
Yes, equal, fine, fine, that is okay. I mean the other part we will have to prove that this is I mean the other way we will have to show that that if this is, I mean if I take strictly equal, then I cannot prove the other way. Okay. Okay. So, yeah, so the I mean basically for the other part only we need this inequality. Yeah, but this is for classical state there is no issue here, this has to be the case, because as I said for classical state this is a valid probability distribution, and therefore, you can take this thing inside. Okay, good. So, let me do the other one. I mean there may be other way of proving this thing, I mean this part, but that is okay. I mean I thought that this may be easier, but the catch is that you cannot do it every time. Okay. So, now let us take so to prove the opposite one, let us take that rho 1 2 is a Gaussian, but non classical state. Okay. So, let this be a Gaussian, but non classical state. Okay. And here if I can prove that the corresponding gamma is not greater than or equal to half 4 cross 4, then we are done, right. Okay. So, this is what we are going to prove. Okay. So, in this case we know that this is non classical. So, this means that this P rho alpha 1 alpha 2 this is singular, right, at some alpha 1 alpha 2, I do not know where, but at least at some point it will be singular. Okay. And therefore, you cannot do this thing here. Okay. Right. Okay, good. Now, how will you achieve such a state? So, this rho which is a Gaussian, but non classical. So, how to achieve this? So, rho 1 2 can be achieved from a 2 mode thermal state, right, which is again Gaussian. So, let us say I call it as rho 1 2 thermal, right. So, any such state, non-classical state, you can achieve from a 2 mode thermal state. This state is Gaussian, this is classical Gaussian. So, okay. How will you get that? Using these three operations. Single mode squeezing, single mode rotation, and beam splitter action, lossless of course, beam splitter action. So, any such state you can obtain by, because you cannot have 2 mode rotation, because 2 mode rotation means it is SO4, and we know that arbitrary SO4 element is not a symplectic transformation. Okay. So, we have this single mode squeezing, single mode rotation and beam splitter action, because 2 mode squeezing can always be obtained by using a single mode, I mean I mean basically a rotation followed by, okay, no, I mean 2 mode squeezing. So, let me look at it, 2 mode squeezing. How will you do that? So, single mode squeezing, tensor product single mode squeezing, here you apply beam splitter, here you apply beam splitter. Okay. So, 2 single mode squeezing preceded and followed by beam splitter action, that will give you 2 mode squeezing. Okay. So, by combinations of these three, these are again Gaussianity preserving operations that we have seen, and beam splitter action, it neither it creates non-classicality nor does it destroy non-classicality, this we have seen. So, therefore, it will not destroy Gaussianity, it will not destroy non-classicality, classicality, fine. So, any such state, non-classical state, Gaussian non-classical state, see, had this been a non-classical non-Gaussian state, our life would have been much difficult. Because this is a Gaussian non-classical state, we can restrict our operations to get the state from a 2 mode thermal state. Okay. Right. Okay. So, now if I look at single mode rotations, in fact 2 mode rotations also, they do not change, does not change eigenvalues, or you can say spectrum of the covariance matrix, right. Okay. Beam splitter action, again because this is a, you can think of it as like a spatial rotation in 2 dimension, I mean in the 4 mode, sorry, in the 2 mode case, okay, because this is a rotation in x1 x2 and p1 p2. So, this does not change spectrum of this thing, okay, right. So, only under this one, single mode squeezing, the spectrum of the covariance matrix can change, okay, right. Okay, good. So, I mean of course, your general action will be combination of this, it is like universal computation. So, you have sequence of actions of these 3 or maybe 2 of them. Okay. So, but whatever be the case, these 2 will not change the spectrum, only this one will change. Okay. So, now let us look at this. So, let us take single mode squeezing. So, this means this is S local, right. I mean, when I say single mode, it is not just only one mode. Okay. So, S local, this is S 1 0 0 S 2, which is basically diagonal of x 1 1 by x and 1 by x, this is 0 0, this is diagonal of y and 1 by y, and here you can take x and y to be positive, right. This is your squeezing transformation. Okay. Right. Now, so what is your rho thermal 1 2? Yes, I mean the covariance matrix of this. Now, according to our this result, this has to be half identity 4 cross 4. In fact, you can check that the for a 2 mode thermal state, this is the covariance matrix. Okay. Right. So, then S local gamma rho thermal 1 2 S local transpose, that is my change state, right. So, this will be your, so this is your half identity. So, basically this will be half S 1 identity 2 cross 2 S 1 transpose 0 0, because this is actually diagonal. Okay. And this is half S 2 identity 2 cross 2 S 2 transpose. Okay. And this is basically your x square by 2 0 0 1 by 2 x square, then this is 0 0 0 0 0 0 0 0, this is y square by 2 0 0 1 by 2 y square. Okay. And let me call it as gamma prime. This is my new covariance matrix. Okay. Of course, you can see that the eigenvalues has been changed. Earlier it was half 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 half, now it has been changed. Okay. Yes, 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 yes. And now, what about this gamma prime plus iota by 2? This has to be greater than or equal to 0 because of uncertainty. Okay. So, if you do that, I am not going. So, basically what you will have, so this is equivalent to this thing, right, x square by 2 iota by 2 minus iota by 2 1 by 2 x square, here it is 0 0 0 0 0 0 0 0, this is y square by 2 iota by 2 minus iota by 2 1 by 2 y square, and now you can figure out that this has to be non negative, this has to be non negative, right. And this will tell you that yeah. So, okay, I mean, yeah. So, basically you will have the eigenvalue equation. So, it will be something like this, lambda square. So, two equations, lambda square minus lambda into x square plus 1 by x square plus 3 by 4 is equal to 0, and this is lambda square minus lambda into y square plus 1 by y square plus 3 by 4, because these are same. Okay. and so you see that you know, this is non-negative, this is non-negative, this is of course non I mean this is positive, this is positive. So, therefore, all the eigenvalues are, I mean, so this tells you that all the eigenvalues, I mean, you know, basically it tells you that all the eigenvalues are non-negative, right, which has to be the case, are non-negative, in fact positive, right. Okay. So, this is fine. Now, what you do is yeah. Now, of course, you know, you can now verify that, and this is not difficult to show that gamma prime, okay, minus half identity 4 cross 4, this is not greater than equal to 0. Okay. So, I mean, which is expected from here, right. So, therefore, you see that if you take a non-classical Gaussian state, it has to be the case that its covariance matrix is you know, it is not greater than or equal to half identity, right. Okay, good. So, yeah. So, therefore, we have proved the theorem. So, therefore, this tells you that gamma of rho 1 2 is not greater than or equal to half identity 4 cross 4, right. Okay. So, yeah. So, this proves the theorem. So, therefore, you know, what we wanted to prove, so the necessary and sufficient condition for the separability of two mode Gaussian state, everything has been proved now. Okay. Right. Okay, good. So, I will not go through the other work of which is this Duan, Gietke, Sirac and Zoller. I will just mention their result. I think, you know, you can take a look at it, and okay. So, let me erase this part. Okay. So, you see that in the opposite case you need to have greater than equal to half identity, okay. So, otherwise it will not work. Okay. Yeah. Okay. So, this is this paper by, which is called as inseparability criterion for continuous variable system. I mean, of course, the title does not reflect whatever is there inside, because this is not the full criteria. So, this is by Loming Duan et al. ERL 84, page number 272220. Okay. Right. So, what they have proved is the following. So, you take A to be a non-zero real number, okay, and then you define this thing, an observable u which is magnitude of A times x 1 plus 1 by A times x 2, and then V is equal to, so this is your definition, magnitude of A into P 1 minus 1 by A into P 2. Okay. So, this is how you define two observables, and then so this is called EPL like operators. Okay. So, so this tells you that for any separable state, rho 1 2, okay, what you can prove is the following, that this delta u square with respect to rho plus delta v square with respect to rho, this is greater than or equal to a square plus 1 by a square. Okay. So, remember in Simon's paper this u and v were more general, because you had this x d which was like d 1 x 1 plus d 2 p 1 plus d 3 x 2 plus d 4 p 2, where d is a real vector. Similarly, x d prime for d prime belonging to R, right. And then we have this uncertainty like this, right, like what we had is delta of x d square rho plus delta of x d prime square rho, which is greater than equal to magnitude of d prime omega d, right. This is something we have obtained for any state, and then for separable state this will be replaced by omega tilde, which is your, this is the partial reflection, right. This is what we have seen. So, this is somewhat they call as EPR like operators. These are called EPR like operators. So, both these papers they consider this kind of operation. This is a special case of this. Okay. So, this is one relation, and then what they have shown is that this is the main result, that a two mode Gaussian state is separable, okay, if and only if yes.
Professor Ghosh,
yes,
the camera has not moved yet to the right board.
is it okay now?
Now it's okay. Yes.
Yes. So, a two mode Gaussian state is separable if and only if yes, if and only if its covariance matrix gamma okay, which can always be taken in the following canonical form under SP 2R tensor product SP 2R, which is like gamma is equal to, this is N1 N2 0 0 C1 0 0 C2, then C1 0 0 C2, and this is M1 0 0 M2, okay, which can always be taken in the. So, if and only if its covariance matrix, it if and only if okay, sorry, if and only if the parameters M1 sorry N1 M1 C1 C2 in its covariance matrix gamma, which can always be written in this form, okay, satisfies okay, now I will have to be careful. Satisfies this thing, delta of u square rho plus delta of v square rho is greater than or equal to a 0 square plus 1 by a 0 square, where a 0 is equal to a 0 square is equal to square root of m 1 minus 1 by n 1 minus 1 is equal to m 2 minus 1 by n 2 minus 1, and u is equal to a 0 x 1 plus c 1 by, not plus, minus c 1 by magnitude of c 1, this is 1 by a 0, this is x 2, v is equal to a 0 p 1 minus c 2 by magnitude of c 2, and then 1 by a 0, then this is p 2. Okay. So, it is something similar. Yeah, here you have this magnitude of A, but instead of that you have this thing. Okay. So, you see that any Gaussian state, two mode Gaussian state, it is separable if and only if these parameters, they satisfy this thing. Okay. Right. So, which is basically this one. Okay. So, yeah, and as I told you some time back that we talked about this canonical form A 0 0 A C 1 0 0 C 2 C 1 0 0 C 2, then B 0 0 B. In fact, you can do again some squeezing etcetera to bring it in this form. Okay. So, yeah, so their result is in this canonical form, but anyway. So, basically you see that the ultimate results are same, but the procedure is different, and as some people say that this one is more experimental friendly for verification, okay, compared to what Simon has done. Okay. So, I think what perhaps I will do next time is I will try to tell you how Simon's criteria can also be verified, at least with some at a first level of experiment. It is not an experimental paper, but at least using optical setup one can verify Simon's criteria. Okay. But whenever but this is mostly with interferometers. So, like the Mach-Zehnder interferometer or some other thing. So, interferometer whenever you do in experiment, the problem is that because it has these beam splitters and mirrors etcetera. So, you always have these kind of noise there, because whenever light hits them, they will start oscillating, okay, and therefore, the interferometric setup is generally not stable, and therefore, whatever you do in interferometer, it's good because it is more this is linear optics, but this problem is there, that you will have this problem of stability. Okay. So, so it is better to use less number of these optical gadgets there in the interferometer. Okay. So, what I will tell you next time is, so the scheme is not optimal, but at least you can use it. And the interesting thing is that maybe I will just erase this part. Okay. So,
Excuse sir.
yes.
Sir, you just now mentioned that interferometer thing will affect stability.
Yes, yes, yes.
So, what that stability means in what context it?
So, you see, like let us say these Mach-Zehnder interferometer. Okay. So, you have these light comes in this is a beam splitter, okay, let us say 50-50 beam splitter, right, and let us say this is also another input beam, and then you have these two output beams, okay, and then you have this reflector, and here also this mirror, and then let us say you again you send this through another beam splitter, 50-50 beam splitter. Okay. So, here you have detector, let us say here you have detector. So, this is the standard Mach-Zehnder interferometer. So, what happens is that whenever light comes, okay, so I have assumed that this beam splitter is lossless beam splitter. Okay, generally that is not does not happen, and to have the exact result of Mach-Zehnder interferometer, what we assume is that these two incoming beams, they should come at a point simultaneously on the beam splitter. Similarly, here they should come at a point simultaneously on the beam splitter. Now, in general that does not happen, and basically whenever you have these lights coming, the lights are here like laser beam or whatever. So, generally due to this pressure, optical pressure, this will start moving like this. Okay. So, therefore, you cannot guarantee that they come at the same point and simultaneously. Similarly here, and same thing happens in the mirrors also. So, they will basically kind of they will have some sort of oscillatory motion, okay, like here and here. So, as a result, unless you bring these two beams together at the point simultaneously, you will not get the desired result. And this is what basically bothers about this interferometric. I mean, this is just a Mach-Zehnder one, you can think of any other interferometric processes, the same problem will happen. Okay. So, the stability is a big deal here, although this is very easy to do, but stability is a big problem. So, you need to take care of. So, for example, in experiment you cannot talk about this is just a single ray, what you need to talk about also is kind of expansion. So, it is a expanded ray. Okay. So, you need to have a beam and waste of that, and then you will have to calculate something here also, and that is not easy. So, whatever we discussed so far, this we have not discussed. So, practically this is what you need to do. So, this is not a single beam, you have always a waste of this beam. Similarly here, so it may be Gaussian beam, it may be some other modes, I mean logarithmic Gaussian mode or whatever. So, this is what makes life difficult. Okay. So, thought experiment wise fine, but actual experiment wise it is difficult, right. Bala, am I sure?
Okay, sir. Thank you.
Yes, Professor Bush. Yes,
Yeah.
That's true, because there are losses and beam should not spread. So we have to make sure that the waves does not
Yes.
change when we do the experiment.
Yes, 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 yeah, yes, yeah. That is what is the problem. Okay, yeah. Is that clear now?
Yes, sir, it is clear.
Okay, okay, good. Yeah.
But why?
Yes. Yeah. What is the question? Hello.
No, actually, sir, that mirror you are saying that it is oscillating, right?
Yes, yes.
That is due to the basic nature of some that equipment, or due to which thing it is oscillating?
Yeah, because equipment you can fix it, that is not a problem. Nowadays you have a good tabletop experiment you can do, but when light is coming they will have a momentum transfer on the mirror, and because of that there will be a motion.
Okay, it's on the light, not due to the equipment.
No, not due to the equipment. Yes, I mean equipment you can fix it, that is not an issue.
Okay. Thank you, sir.
Thank you. Yeah. So, what I think next day what I am going to talk about is I will use the Simon's criteria. I mean the separability criteria. For two mode Gaussian state. So, what I will try to convince you is that, so give, so let us say this is my source which provides me a rho 1 2 which is a two mode Gaussian state. I mean it will not be a single ray, but anyway, point is that I do not know what is this, I only know that this is a two mode Gaussian state. So, that means I do not know its, so do not know gamma, also do not know this mean values. Okay. Because I cannot assume that these are all zeros. So, I only know that this is a 2 mode Gaussian state, and then I will use the Simon's criteria. Of course, I will have to modify it little bit to show that rho 1 2 is separable or entangled, and this is mostly interferometry based. Some nonlinear gadgets we will have to use, and this is why you can call it as universal detection of entanglement in any in 2 mode Gaussian states. Okay. Universal in this sense that you do not need to know what are this, and for Gaussian state this is enough to know, right. If you know this thing, you know the Gaussian state. Okay. Now, so this is what I will discuss next time, because it requires this. I think I will give PowerPoint, because I will not do it on board, because I have slides I can do that. So, the point is that why this is interesting. If you take a 2 qubit state, let us say rho 1 2, okay, a 2 qubit state, then we know that rho 1 2 is separable. This is equivalent to saying that if I take its partial transposition, maybe with respect to party 1 or party 2, this is greater than or equal to 0, right. This is the Perez-Hordodecki criteria. This is also equivalent to saying that determinant of rho 1 2 partial transposition is greater than or equal to 0. So, it means that whenever rho 1 2 is entangled, then rho 1 2 partial transpose. So, basically it tells you that rho 1 2 is entangled. This is a 2 qubit state. It means that rho 1 2 T 2 has one and only one negative eigenvalue and rest 3 are strictly positive. Because in that case only you can take determinant of rho 1 2 partial transposition, that will be negative, okay, right. So, this is the case for 2 qubit states. Now, if I look at Simon's criteria, it tells you that 2 mode Gaussian state is separable if and only if rho 1 2 T 2 is greater than or equal to 0, right, for any 2 mode Gaussian state, right. So, this is equivalent to separability of rho 1 2. This is what Simon's criteria tells me. In fact, these criteria are also similar, but that is okay. So, one might think that this is somewhat similar to the case of 2 qubits, right. So, the question is that now in this case we know that there exists a Hermitian operator W, which is acting on C2 tensor 4, then C2 tensor 4. Okay. So, that means this is what? This is your 4 qubit, this is also 4 qubit. Okay. So, you can find out a Hermitian operator such that determinant of rho 1 2 T 2, this is I am talking about the 2 qubit case. Okay. this is equal to trace of W rho 1 to tensor 4. Okay. So, this one can figure out, one can show that for a 2 qubit case. So, what does it mean? It means that if I, so this is a Hermitian operator and you are measuring this Hermitian operator on these 4 copies of your 2 qubit state, right. Now, if this turns out to be negative, then you know that the original state is entangled. If it turns out to be non-negative, you know that the original state is separable. So, just by measuring this a single observable on 4 copies of this state, you can detect whether the state is 2 qubit state is entangled or separable, just one observable on 4 copies. So, the question was, the question was that whether similar thing can be done here for the case of 2 mode Gaussian states, whether one can come up with a single observable, so that it may not be 4 copies, maybe more copies, but whether some such thing can be done. Okay. Unfortunately, for the case of 2 mode Gaussian state, the separability criteria, although it is in this form, but you cannot cast it in terms of like determinant condition like here, you cannot do that. Okay. And therefore, it is not so straightforward, but still one can show that you can have some interferometric setup with a little bit of non-linearity. Interferometry does not use non-linearity. You can come up with this universal detection. So, I cannot tell you that what is this single observable, but one can provide interferometric setup to show that. So, therefore, operationally you can say that yes, similar thing happens in the case of 2 mode Gaussian states also. Okay. Yes. So, yeah, this is what figure out what. So, this is you need to look at the so you need to look at this what is that called this eigenvalue decomposition, what is that called, Cayley-Hamilton theorem, or what is that, this you write down the eigenvalue equation. Okay. So, in the coefficients you can write in the eigenvalue equation in terms of I think the some functions of powers of the matrix. Okay. I mean the okay. So, by using that you can figure out this.
So, it depends on the rho 1 2.
No, it does not depend, sorry, it is not like that. Let me see, how do you figure out? No, it is not, it does not depend, it does not depend upon rho 1 2. So, there is a way of finding out, maybe I will tell you how to do that. So,
Are we saying there is a universal Hermitian operator that works for any qubit?
yes, any 2 qubit state. So, this has no information about rho 1 2. Okay. So, this is very experimental friendly, okay, because you set up your experimental facilities only for this and then this will work. So, actually we wanted to do similar thing for 2 mode Gaussian state, but one cannot come up with just one operator, but anyway the setup is similar. Okay. Yeah. So, my problem is that such a criteria does not hold good if you go to higher dimension, for higher dimensional states. Okay. For Gaussian state is a special case, 2 mode Gaussian state. So, that is why it works. Okay. So, okay, yes. Yeah, in fact, what one can do is this, you can also lift it. So, here you will have to set up your experiment to measure these operator, right. So, you should have some detectors and all that, right. Problem is that whenever you have those detectors, these are basically photon you can consider these photon polarizations, you know, as so like 2 photon polarized entangled state for example. So, then you will have detection inefficiencies, right, for detecting, I mean for performing measurement of this. So, what happens is that because of these detection inefficiencies, sometimes a separable state can become entangled, right, because you know if you have detection inefficiency for separable state, ideally it should be non negative, but it may turn out to be negative. Okay. So, there is something called, you know, what is that called in cryptography, we often use it like this, what is that called, this photon attack or something, where you you know in coincidence count the 2 photons should come together and then somehow eavesdropper will delay 1 photon. Okay. So, that you will not get the coincidence count. Okay. So, there is something called, what is that name, I forgot anyway. So, some such attack can be there and therefore, you will not get. So, what may happen because of these errors in the detection, this a separable state may turn out to be entangled, and which is very dangerous. Entangled state turn out to be separable, fine, okay, but separable state turning out to be entangled is very dangerous, because you cannot use that. So, but what one can do is you can modify this method, this process, to a something called measurement device independent scheme, where even if there are errors in the detection, still no separable state will become will appear to be entangled in that measurement device independent scheme, right. So, so this can be done, and I think people have also done similar thing for 2 mode Gaussian state, measurement device independent scheme for detecting entanglement in 2 mode Gaussian state. So, yeah, so these things are basically important from practical perspective. Okay. Okay, I think I should stop here, and then next day I will give that you know the scheme for universal detection. Okay.